All right, so this is going to be a lot different than the talks this morning. This is going to be more about kind of how we used LLVM. In a lot of ways, we're much more kind of an LLVM consumer than a producer, so it's from a different perspective. And hopefully it won't be too kind of graphics and image processy to hold your interest, but that's kind of where we're coming from. So, all right, so let's see. So Adobe Image Foundation is the name of our team, and it's a piece of technology for performing basically data parallel image processing computations, trying to use all the system resources that are available for this. And the goal is, it's kind of motivated from kind of, hey, what can we do with graphics cards kind of point of view. PixelBender is the name of our little language, which is kind of a derivative of GLSL, HLSL type languages with some additional sort of stuff put in there for image processing that allows us to allow third-party people to author kernels without having to author any kind of anything that's compiled down to an executable ahead of time. So, all right, I had a couple disclaimers in the interests of full disclosure. There's some stuff I can't talk about today. And in particular, the chief thing among them is where Adobe Image Foundation or PixelBender will appear in as yet to ship products. It's under development for being used by a number of people, but I'm not allowed to spill the beans on which things are using us in the next go around. PixelBender, or excuse me, actually PixelBender is used in a closed sort of non-third-party friendly fashion in After Effects CS3, which is a video post-production suite. And that's where we are currently. And we have a toolkit that's available on the web. I'll put the website for that up later. Okay. And I like LLVM. At some point I'll talk about a few things that could have been more helpful. But those are from the perspective of a very friendly person. So, all right. So the motivation for our whole project is GPU proliferation. So at the beginning of time, graphics cards were fixed function. You could do things like texture, lighting, transformation, depth. A lot of cool stuff you could do with that. These things started to like come down to the PC space. You had the early D3D cards early cards that could run things like Doom, sort of accelerate that a little bit. And you had a quick draw 3D card, as a matter of fact. I had one of those back in the day, and kind of like that language too. But programmable GPUs started to take over, and at first it was little tiny ASM-like pixel programs, and then you could add per vector programs, and largely this kind of obliterated most of the fixed functionality of a graphics card, and pretty much all graphics is now done using programs that are run at on a per vertex basis or a per pixel basis. And the ASM programs gave way to things like GLSL, HLSL, CG, and multipass frameworks like the effects system at Microsoft. And then the latest kind of round of things is things like CUDA for general purpose GPU, CUDA, CTM, kind of the graphics card vendor solutions to that problem, and OpenCL, and DX Compute Shader, which was announced last week at GameFest, are the kind of OS vendor solutions to the problem. But of course at Adobe, everyone is thinking, hey, can we use GPUs to do stuff that we really care about, like image, video, and et cetera processing? Okay, so that's just my spiel. I love games, and I'm really happy they're useful for other things now, GPUs, but we owe a debt of thanks to the gaming industry to making basically everybody has a super powerful parallel computational device on their desktop or laptop now because of people playing Quake. And and this is us, Adobe Image Foundation, and here's our language. So I'm going to start off by sort of how the talk's going to progress. We're going to look at PixelBender sort of as the identity filter first, and then talk a little bit about that, and then I'll sort of give you the sort of basic overview structure of the language, and then we'll move on to here are some kernels, and if I have time to do a demo, and talk a little bit about the how we translate to LLVM, and then some of the issues we found in sort of security, stability, things that kind of came up in the development process. All right, so here's our identity filter. So sample here is bilinear interpolation. Don't really need to know that, but it's a fairly heavyweight operation actually done in hardware on GPUs, but of course on CPUs we have to code it up. So we have kernels. Everything we do is in a kernel right now. Evaluate pixels, kind of a special function. This function gets run for every single pixel that's produced on the screen. That's how graphics is done these days. We have input images of various channel depths and also channel orderings, RGB, DVR, 32-bit, 8-bit, 16-bit. We produce pixels of various channel orderings, or excuse me, channel depths, and then here's your identity. So the destination pixel is going to be the bilinear sampling of the source image at a particular out coordinate. So really simple. All right. So to recap, programs are written to produce pixels. We have input and outputs, and these are globals. First glance, it looks a lot like GLSL. And so you might wonder, like, why is Adobe inflicting a new language upon us? And in fact, there's a lot of stuff about image processing that doesn't really fit into the GLSL model. In particular, there are things that happen on the frequency of a frame before a frame starts to calculate, as opposed to the things that happen on a per pixel basis. And GPUs aren't really good at dealing with things that happen on a per frame basis. And so we have ability to specify bits of code that run prior to the pixels getting executed. Also, the entire kernel lives in the PixelBender program, and this includes all the per frame setup and various things. And this allows a third-party author to write a PixelBender program and then hand it into a system and have it run as a plugin without having to code up an executable, which is pretty useful from making the third-party developer sort of world happen. All right, so here's to show a slightly contrived per frame function example. So the idea of this filter is to do the negative of the RGB channels and leave the alpha channel alone. So we do this weird little funky thing. We have a parameter. So that's going to be an input to the per frame functions. And dependents are things that are produced by the per frame functions, but which are constants at the evaluate pixel stage. So we have this little, we set up basically a float value to determine this S value. And then we do a sort of a linear interpolation of the negative of the pixel or the pixel based on whether or not it's negative or not. This is kind of a curious way to write it. And admittedly, it's a bit contrived for the purposes of this slide. But it's actually not a stupid way to write it, because graphics cards, at least not the latest crop of graphics cards, to do an if, that's how they do an if. They